So in a statistical study, you will prepare, analyze, and then conclude the study. We'll be going over that in much greater detail. So there are different types of studies. Some are, well, there are qualitative studies and there are quantitative studies. So qualitative studies are ones in which it's a very organic type of study. It is a study where the questions that will be asked are really found during the study. It is done by asking people questions and then exploring where these questions lead. In quantitative studies, it's much more linear. You start out with a question and you figure out, well, what do I need to do to answer this question? And so there are different types of quantitative studies, such as, well, observational studies and experimental studies. So let me give you different types of observational studies. So a cross-sectional study. In a cross-sectional study, data is observed, measured, and collected at one point in time. In a retrospective study, or in a case control study, data is collected from, well, you first do the study and data is collected from the past. So you will look at some cases, let's say. So you'll look at people that have a certain disease, and then you go and look back. Well, what are their different exposures? And so you'll try to figure out, well, is there some commonality in the exposures of people with the disease that is different from people who do not have the disease? So you may want to, if you have some disease and you don't know what has caused the disease, you will use this case control, where you look at a whole bunch of people with the disease. Those are the cases. And you look at people that do not have the disease, the controls. And then your data is collected by going back in time. So you examine records, interviews, you look at what is their environment, what do they eat? You know, you basically look at everything and you try to see, is there anything that I can glean from this data? So it's either called a retrospective study or, well, actually, what I just described was a case control study. A prospective study or a longitudinal study, sometimes just called a cohort study. In a prospective study, you look at data, you look at your object, and then you go forward and see what happens. And so let's say in a cohort, you would have a whole bunch of people that looked identical, a whole bunch of subjects that somehow looked identical. Then you would have some sort of exposure, and you would look at what happens in the future. So you would keep, maybe you would come back a year later and see if any of these people, any of these subjects, well, they don't have to be people, any of these subjects happen to have a particular disease, and you keep periodically checking back on them and see if there's some disease that arises from a particular exposure. Okay. So, an observational study. So, in an observational study, we observe and we measure, but we do not modify. So, we're just observing these exposures. We're observing and measuring, if they get a disease or if they don't or whatever, we're interested in. So let's ask the question, well, when are observations made? If they're made in the, in the past, then this is a retrospective study. If they're made currently, then this is a cross-sectional study. If they are done forward in time, this is a prospective study. Please note that if data is not collected in an appropriate way, the data might be so completely useless that no amount of statistical torturing can salvage them. So it's very important that data is collected correctly. In this course, we will assume, well, after the next section or two, we'll assume that all of our data has been collected appropriately, and we will study it. In your subsequent courses, especially in your major, you will be looking at differing ways to correctly collect data. So, statistical methods are driven by the data that we collect. So, we'll either be doing statistical, observational studies or experiments. And so these are called quantitative studies. So there are also these qualitative studies, but we'll not focus on them. So, again, an observational study. We'll be observing and measuring specific characteristics without attempting to modify the subjects being studied. An observational study is also called a quasi-experimental study. It is an experiment in which one observes how a treatment has already affected or will affect subjects. So in an observational study, we observe and measure specific characteristics, but we don't attempt to modify the subjects being studied. So let's do an example. The Pew Research Center surveyed 2,252 adults and found that 59% of them go online wirelessly. Is this an observational study? Well, we are just observing if they go online. We are not in any way trying to modify how they go online. Therefore, yes, this is an observational study because there was no treatment that was applied to these subjects. We just observed them. So yes, this is an observational study because the adults had no treatment applied to them. So an experiment. And so in an experiment, you apply some treatment and then observe its effects on the subjects. The subjects in an experiment are called experimental units. So in an experiment, we apply some treatment and then proceed to observe its effects on the experimental units. Okay, so let's do another example. In the largest public health experiment ever conducted, and this is actually a true statement, actually it was even going to be larger, 200,745 children were given the Salk vaccine. So the Salk vaccine was a vaccine against polio. So polio was a, well, still is, let's see. Oh, I have a question. Oh, someone says I have a question. Okay, what is the question?
Okay, you said that or observational study, it's how one observes and
Does not modify.
But that does not modify. But it says how a treatment has already affected or will affect the subject. So does this mean the observational study can be retrospective or prospective study too?
Yes. Yes. So yes, you can either be retrospective. So observational studies can be retrospective, meaning it's gone in the past, or prospective, meaning it's gone in the future. And you can have a cross-sectional study. So say that you look at people with cancer, with lung cancer. So you look at people with lung cancer and you look at their records and see, well, what was in common? They smoked, right? You can then do a study where you say, okay, I want to figure out how many people are currently smoking. That's cross-sectional. Now you could also do prospective, where you say, okay, well, look, I'm going to look at all these adults, and they all look healthy, etc., and they all have, and they all have the same environment, except some are smokers, some are not smokers. And then every 10 years, I'll look and see how many of them get lung cancer. So that's a prospective.
So does this mean that, yeah, it does, but does this mean also that the experimental studies can also be retrospective and prospective?
Experiment, no, because you're giving a treatment. So in that case, you're actually giving them a drug, right? So you can't look in the past for the effect of a drug because you never gave it to them. So, okay. And usually the thing that you're giving them, the treatment, is usually a treatment that is done at the end of the experiment. So even though it's quote unquote forward in time. So you give them a treatment, and then at the end of the experiment, you look and see how has the treatment affected these subjects. Okay, that's not called prospective because it's the end of your experiment.
So
Okay?
basically, experimental is what is currently happening at that moment, and
Well,
observational
yeah,
is
it's what happened during the treatment. So the
during
treatment
the
may
treatment.
take
Yeah.
your treatment may take a while. So you may have, maybe you're giving them sort of drug, some pharmaceutical treatment, and at the end of it, you want to see, well, does it help? Does are these people now treated for this particular disease?
Okay.
So it's not like we're talking about forward in time or backward in time or whatever. We're just saying that we've conducted an experiment. The experiment obviously has to take some time. And we are giving a treatment. The treatment may take time or whatever, but it's a treatment. We've given a treatment, and the treatment may involve a particular time, but that's sort of the clinical boundaries that you need for that particular treatment. Okay.
Okay. Okay.
Okay. So let me go back. So the Salk. So the polio. So polio is caused by a certain bacteria. No. So bacteria. Polio, it's a vaccine, so it's a virus. I thought it was, okay, so polio, oh yes, yeah, it's a virus. So polio is caused by a certain virus, and it would affect mostly children, but adults also, but usually mostly children during the summer. And so large numbers of usually young people, usually people in their teens, would be affected by polio. And usually it causes paralysis. And depending on where the paralysis is, usually maybe the paralysis is of the lungs, where they are then usually unable to breathe. And it's usually people, once they have that paralysis, they never recover from that. And so they always have that particular paralysis. So some large number of people affected by paralysis would then have to be put into things called iron lungs, things that would breathe for them, basically for a lifetime, or they would be crippled for a lifetime. So it affected a large number of mostly young people, sometimes adults. So the majority of people that were affected were they were teens. People in their teens were mostly who was affected by this during the summer. And only a very small number, things like Roosevelt, he was affected when he was in his 30s or late 30s, early 40s. So there are a few people that were affected later in life, but the vast majority were affected during their teens. So because of this, there was actually a big movement to see if it would be possible to eradicate, not eradicate, but to find a cure for polio. And so they started this campaign where they tried to get everyone to donate a small amount of money. And so it was called the March of Dimes. I believe that that organization still exists. So it's called the March of Dimes. And so they would try to have people give a dime and donate a dime to eradicate, to stop polio. And so as a consequence of this, there were actually two vaccines that were that came out of this effort. One of them was the Salk vaccine. And so one was the Sabin and the other was the Salk. Named after people. Sabin, named after Sabin and named after Salk. And so in the largest public health experiment ever conducted, 200,745 children were given the Salk vaccine. Another 201,229, 229, so 201,229 children were given a placebo. Is this an observational study or an experiment? Since they were given a treatment, this is an experiment. And so any sort of treatment, in this case, a vaccine was administered. They were given a injection, right? Vaccine, yeah. So the Salk vaccine was an injection. The Sabin is oral. I believe Sabin is oral. And so they were given to subjects. So since there was a treatment given to a subject, then this is an experiment. So actually the experiment was to give it to basically, I think there were supposed to be like 10 million people that were in the experiment. But it was stopped because it was found that it was so effective that they actually stopped it very quickly. So this is why only 200,000 people, 200,000 children were given the placebo because a lot of those people given the placebo got polio, and virtually no one in the, that got the treatment actually got polio. So they stopped the experiment very quickly and said, okay, everyone's getting the vaccine. So the vaccine injection constitutes a treatment that modifies the subjects. So this is an example of an experiment. So a response variable. A response variable is the variable being studied by the observer. And so in this case, the response variable is if they get the disease or not. So the treatment was the vaccine, injection was a vaccine, and the response was, well, polio. So experiment. An experiment investigates how the response variable behaves when the investigator manipulates one or more factors. Any particular specification of such factors is called an experimental condition or a treatment. So a treatment, experimental condition. A particular specification of a factor is called an experimental condition or treatment. An experimenter actively intervenes by controlling the environment and administering treatments to subjects in order to study their effects on the response variable. Extraneous factor. And so an extraneous factor is a variable that is not of interest in the current study, but is thought to affect the response variable. In cohort studies, we usually use, so in cohort studies and in experiments, we use, so in both, this is what happens here. Okay. So cohort studies and experiments use cohort studies and experiments use extraneous factor to create experimental groups that are similar with respect to those factors, thereby filtering out their effect. So if an extraneous factor is thought to exist, then those factors are used to create groups. So let me go over how to design experiments. So randomization is one technique that is used in the design of experiments. Randomization is used when the subjects are assigned to different groups through a process of random selection. And so somehow we create groups using some chance method to determine these groups. So in comparative experiments, subjects are assigned to groups randomly, and this is called randomization. Replication. And so one of the important things with an experiment is once you've done an experiment, is can you replicate the results? So replication is a repetition of an experiment on more than one subject. So samples should be large enough so that the erratic behavior that is characteristic of very small samples will not disguise the true effects of different treatments. Use a sample size that is large enough to see the true nature of any effects, but not too large so that it becomes unyielding to actually do an experiment. And you obtain the sample using some sort of appropriate method that gives you some representative sample, such as using randomness. So a comparative experiment. In a comparative experiment, the group of subjects is randomly divided into two equivalent groups. The experimental group that receives the treatment and the control group that does not receive the treatment. And so the placebo effect. So the placebo effect is when a subject in the control group has a positive response to a treatment, even though it was not given to the subject. And so somehow the subject in the control group has a positive response to a non-treatment. So let's see, the John Hendry effect is when, oops, somehow that disappeared, is when when subjects will modify what they do, thinking that they have a treatment. And so just the fact that they are in a particular experiment, they modify their behavior. So that's the John Henry effect. I can't remember the other one. Okay, so to deal with that, we have a technique called blinding. There's more than one technique, but I'll just discuss blinding. So blinding is a technique in which the subject doesn't know whether they are in the treatment group or whether they're in the control group. They do not know if they're receiving a treatment or not. And we could either blind the subject. So it's a technique in which the subject or the experimenter does not know if they are in so blinding is a technique in which the subject or the experimenter doesn't know whether the subject is receiving a treatment or a placebo. So blinding allows us to determine whether the treatment effect is significantly different from the placebo effect, which occurs when the untreated subject reports an improvement in symptoms. So a double-blind experiment. In a double-blind experiment, a double-blind experiment is a comparative experiment in which neither the subjects nor the researcher knows which subject will receive the treatment and which will receive the placebo. So this is called a double-blind experiment. So blinding can occur at two levels. One level is with the subject. So the subject does not know whether they are receiving the placebo or the treatment. And at the second level, it's at the experimenter level. The experimenter does not know whether he or she is administering the treatment or the placebo. And actually the third part, there's actually another part, I guess, is where the experimenter observes the effects of the treatment. And so they don't know if the effects that they are observing is due to the treatment or a subject that does not have the treatment. So confounding. Confounding occurs in an experiment when the experimenter is not able to distinguish between the effects of differing factors. So you should try to plan an experiment so that confounding does not occur. So a confounding variable is one whose effects on the response variable is mixed within the effects of the treatment. So confounding occurs in an experiment when the experimenter is not able to distinguish between the effects of these different factors. So how do we control the effects on these variables? So completely randomized experimental design. In a completely randomized experimental design, subjects are assigned to different treatment groups through a process called random selection. In a comparative study in which subjects are divided into random groups, this is called randomization. So a random block design. In a randomized block design, you will design a block, which is a group of subjects that are very similar. But blocks differ in ways that might affect the outcome of the experiment. So within the block, they're homogeneous, but the blocks are heterogeneous. So a matched pair design. In a matched pair design, you will compare two treatment groups using subjects matched in pairs. I usually think, and so that somehow they have similar characteristics. So usually in matched pairs design, I always think of a situation where you are maybe, you have some diet that you're on. And so you look at before the diet and after the diet. And so what you're comparing is the after, which is usually the same person. So I'm looking at me after I've been on the diet and compare it to before I was on the diet. And so I'm comparing those two groups. So in comparative experiments, after groups have been selected, each subject within each group is paired up with an equivalent subject from the other group. So in this case, they're matched up with themselves. And so you can match yourself. So you can say, well, before and after. So a rigorously controlled design carefully assign subjects to different treatment groups so that each treatment are similar in ways that are important to the experimenter. So, in summary, there are very important characteristics to consider in the design of experiments. One, you should use randomization to assign subjects to different groups. Two, you should use replication by repeating the experiment on enough subjects so that the effects of the treatment or other factors can be clearly assigned. Three, you should control the effects of variables by using such techniques as blinding and a completely randomized experimental design. So, errors. So let me discuss briefly some errors. So no matter how well you plan or execute a sample collection process, there's likely to be some error in the results. First, sampling error. So sampling error is the difference between the sample result and the true population results. Such errors result from chance sample fluctuations. And so there is, and these occur naturally. And so just because, if you have a population in the United States and you ask two people, if you get the results, if you ask two different people, you'll probably get a different result. And so there's going to be some fluctuation because you're not asking everyone, you're asking a sample. And so there are ways to control these and to detect how you expect what these fluctuations shall be. So these are controllable errors. or these are errors that can be, these are, let me restate, these are quantifiable errors. So these are quantifiable. Non-sampling error. So non-sampling error occurs when sample data is incorrectly collected, recorded, or analyzed, such as by selecting a bias sample using a defective measuring instrument or copying the data incorrectly. So one of the jobs that I had in a previous life was heading the math assessment office. And in that capacity, I had access, actually I was the only person in the district, I guess, that had complete access to all records of all students. So yeah, I guess I was, actually there were two people. So I was one of two people that had access to all of the records of every student, oops, in the district. And so, let me turn that off. Okay. Okay, there. And so because of that, since I was privy to all that information, what I did notice is that, especially in a school, once you have put something into your database, it's virtually impossible to get rid of it. You can't, basically no one has privileges to change student records. We can observe student records, but we can't change their records. We can keep adding things to their records, but deleting things from records is nearly impossible. Students can't, well, students can, I don't even know if students can request it. Basically, once it's in there, it's in there. And I don't know if anyone has the authority to change it. And unfortunately, what that means is that your database gets more and more corrupted the longer it is. And so what I did notice is that with things like students' ages, there are certain birth dates or whatever, they had the weirdest sort of things that were included in it. So there were students that were, you know, their age was, you know, billions of years old. Well, yeah, so hundreds of millions of years old, and their birth dates were, you know, similarly, and you know, all these weird sort of things. Usually, what happens is that when students are entering in information, they enter it in and they don't really notice what they're entering in. So a lot of times they put in their social security number when they're asking for their birth date, or their phone number when they're asking, you know, when they were born and things like that. So usually what happens is you'll notice that there are a large number of places where the data is obviously not correct, because they're, you know, especially with people's ages, you can tell if people have negative ages or ages more than 1,000 years old. You know that those are incorrect. Ages. So there's, and it turns out that there's a lot of that. Okay, so, and of course, sometimes people just, you know, type in things incorrectly. They'll transpose numbers or whatever. It's very easy. Okay, so non-random sampling error. So the result of a sample method that is not random, such as a convenience sample or a voluntary response sample. So you could have some error, and the error is because you're not collecting a random sample. Well, let me talk, so epidemiology. Epidemiology is the study of the distribution and the determination of health and health-related states, let's say, or health-related events in some specified population, and its application to control these types of issues. So, a properly designed survey reports the following: a description of the sampled population, a description of the method of contact, the response rate, the exact wording of the questions, the timing of the interview, the size of the sample and the margin of error, the sampling technique. So the following factors should be considered when you have a survey results are studied. So your population, your method of contact, response rate, the wording of the question, the timing of the interview, and the sample design. So to conduct a sample survey, decide what information is needed, what questions are to be answered, and you must identify your population. Determine how the data will be collected. Phone interview, mail survey, some other type of survey, published, source, design, experiment, survey, observational study. Step 3, select the information gathering instrument or design a questionnaire if one is not available. Step 4, set up a sampling list if possible. Step 5, select the best method for obtaining sample, a random sample, systematic, cluster, stratified, things of that sort. Conduct the survey or sample, conduct the survey or experiment and collect the data. Tabulate the data, conduct statistical analysis, report the results, describing the population, method of contact, response rate, exact wording of the questions, timing of the interview, size of the sample, margin of error, design of experiment, and the sampling technique. Oh, I should say that. So, when having a experimental question, you should have the population, the intervention, comparison, and the outcome. There, PICA, there. So you should have some population in which you're intervening something, and you're going to have some sort of comparison. And then once you've done that, you will then observe your outcome. There's also sometimes we have to talk about time. Okay, so a statistical survey study. So first you should prepare, then analyze, then conclude. So you first compare. So you look at the context. So what does the data mean? What's the goal of the study? Next, the source of data. Are the data from a source with a special interest? So there's pressure to obtain results that are favorable to the source? Is the source objective? Is the source biased? So you should be vigilant and skeptical of studies from sources that may be biased. Sampling method. Were the data collected in a way that is unbiased, or was the data collected in a way that is biased, such as a procedure in which respondents volunteer to participate? Does the method chosen greatly influence the validity of the conclusion? So note, voluntary response or self-selected samples often have bias. Those with a special interest are more likely to participate. So other methods are more likely to produce better results. So analyze. First step, you should always graph the data. So every analysis should begin with the appropriate graph. So we're going to be looking at graphs starting in chapter 2. Next, you should explore the data. So first question is, are there any outliers? Are there any numbers that are very far away from the vast majority of the other data? Next, what are the important statistics that summarize the data, such as the mean, the standard deviation, other things that we'll be describing later today, or maybe next week. So how is the data distributed? Is it all bunched together? Is it spread out? Is there missing data? So no matter what you try, there's always going to be some things that are missing. Did the subjects refuse to respond, and so, or refuse to participate after a particular instant in time? So you should apply statistical methods, use technology or computations to obtain your results. So later we'll be talking about these statistical methods. So with not technology, a good analysis does not require strong computational skills, but does require a statistical sense and paying attention to sound statistical methods. This statistical sense will be accomplished through the use of simple examples and mathematical arguments. So, conclude. First, you have to look at statistical significance. So there is a technique that you'll be learning later in this course. And so, do the results have statistical significance? So statistical significance is achieved in a study when you get a result that is very unlikely to occur by chance. Practical significance. The results have practical significance. And so state the practical implications of the results. Common sense might suggest that the findings do not make enough of a difference to justify its use or to be practical. So in one of the things I was looking at recently, so Alzheimer's disease is a fatal disease. Basically, everyone who gets Alzheimer's disease will eventually perish from the disease. It's a neurodegenerative disease. So it's a disease where your the size of your brain shrinks, and there are these amyloid plaques, these small little things that are in between your nerve cells, your neurons in your brain that are formed. And there are these neurofibrils, these things that occur, these tangled proteins that occur inside your nerve cells, your neurons, and it causes degeneration of your nerve cells and death of your nerve cells, which causes, first starting off, memory loss, changes in your behavior, and eventually death due to neurological damage. Its course is usually about 25 to 30 years. So it's a very slow acting disease. Most people get it starting in around age 50. But the first 20 years are asymptomatic. First 15, 25 years are asymptomatic. Usually by the time symptoms occur, usually with dementia, usually 3 to 5 years is sort of the, how long people would survive with the disease. So currently there are only like 4 pharmaceutical treatments for it. There are these cholinesterase inhibitors. And so they are statistically significant in prolonging the duration of this disease. And so if you go through and do statistical results, they're statistically significant. And so they've been approved by FDA, but they're not practically significant, meaning that how long they extend the life of a patient is usually, I believe it was 1 week. So it's statistically significant, but not practically significant. In a disease that lasts 30 years, a 1 week extension in the lifetime is not really practically significant. But of course, the usefulness of it is that it does alleviate some of the symptoms, and the toxic effects are relatively moderate for the pharmaceuticals. Okay, so example. In a test of the Atkins weight loss program, 40 subjects had a mean weight loss of 4.6 pounds after 1 year. So using formal methods of statistical analysis, we can conclude that the diet appears to be effective. However, although 4.6 pounds is statistically significant, it does not seem to be very worthwhile. So if you have, let's say that you are 50 pounds overweight, then that means that it will take you 10 years to actually lose that weight, that excess weight. So, potential pitfalls. So, misleading conclusions. concluding that one variable causes the other variable, when in fact the variables are only associated with each other. They're only correlated. So there may be some association, but you cannot do a conclusion. And so two variables that are linked are smoking and pulse rate, but we cannot conclude that one causes the other. So correlation imply causation. Another potential pitfall is small samples. So conclusions should not be based on samples that are too small. So based on a school suspension rate of a sample of 3 students. So 3 students turns out not to be large enough. Now, here, wait 1 second. Here, if we look over here, wait, what was the one? Oh, that was probably in the previous one, where they did 1,000 people. Okay, so here, wait 1 second. Let's see if I can. Ask this question. Oh, here it is. So here's a question. So on the previous, in section 1.1, we had this question where there were 1,000 adults that were asked by the Gallup Corporation. The Gallup Corporation is really a corporation that does statistics. And so they collected data from 1,013 adults in the United States. So the question is, well, there are 200 million adults in the United States. Is 1,000 large enough? What do people think? Later in the course, we will see what the size, what you should have as the size of a sample. Does 1,000 seem like enough? Or is that too small? Anyone? Is anyone awake? What do people think? Is 1,000 enough? Or is that too small? Too small, okay. So someone says too small. Does everyone agree? Is it too small? So one person was brave enough to answer. Okay, so it turns out that actually 1,000 is okay. So it turns out 2 is too small, but it turns out that actually 1,000, 2,000 is large enough for everyone in the United States. So it turns out that if you look at samples done by, say, political polls or whatever, if you look at their sample sizes, it's always around 1,000, somewhere between 1,000 and 2,000. Why? Well, we'll tell you later in the course. So it turns out that that is actually the proper sample size. So to me, it looks too small. You know, you only ask 1,000 people, there are 200 million people, right? But in reality, that actually is a sufficiently large sample. So it actually turns out that that's probably a sample size that's okay for answering this question. So, but later on in this course, we will actually figure it out. Okay. Let's see, where was I? I highlighted it, so, oh, there it is back there. So we'll actually be able to quantify what I mean by small. So, so in this case, 3, because certainly I can say 3 is too small. Okay, so 3 is certainly too small, unless the school has like 4 students. So unless the school is really tiny, 3 students is certainly seems to be too small. Another potential pitfall. Loaded questions. So if a survey question is not worded properly, the results of the study can be misleading. So they did a study, and 97% answered yes to the following question. Should the president have the line item veto to eliminate waste? By the way, this was actually a result that I saw, and I noticed that they had another survey that they did by a different corporation, and they said 57% responded yes to the following question. Should the president have the line item veto or not? So if they ask it, should the president have the line item veto to eliminate waste, everyone agreed. Whereas it was not nearly as positive when they asked the question, should the president have the line item veto or not? And so I consider that as a loaded question. They are trying to steer you to the answer that they wanted.
Professor, I have a question.
Yes. Mm-hmm.
On the potential pitfall of a small sample, what about if the population is around, let's say, 10 people?
Yeah.
If the sample is still small, if you take 3 of them?
No. Yeah, that's what I was saying. If the school was really small, like it only had 4 students or something, or 10 students, then maybe a sample size of 3 is okay. So if the population is really tiny,
so basically the potential pitfall, it would depend of the amount of the whole population to be considered small or not.
But barely, meaning the following, that once the sample size is smaller than 5% of the total population, the population size really doesn't make a difference. So in other words, 3 students is okay as long as there's only like 12 total. But once you start getting more than 15, a school of 15 or more, then 3 turns out to be small. So as long as it does depend on the population, but not as much as you would think. So there is an effect for the population, but only you really only have to consider that when your population is really tiny. Okay.
Okay.
And we will have there's a finite population correction term. There is a way that we will quantify that. So for right now, I'm just sort of saying, well, that looks small, and but I'm not putting numbers to it. But we will. So eventually, we will have enough stuff that we know that I can actually answer this question better, because I'll actually be able to quantify it, what I mean by this. Okay? So another potential pitfall is the order of the question. And so sometimes that can be misleading, and usually it's usually when you do this, the person who writes it doesn't even know that that it's a pitfall. So usually what happens is that this is unintentional, but it does work. It does happen, but it's this unintentional sort of bias that occurs. And so sometimes questions have to be given in a slightly different fashion to see if this is occurring. And so we have the following results. Would you say that traffic contributes more or less to air pollution than industry? So 45% said traffic, 27% said industry. Next, when they asked, would you say that industry contributes more or less to air pollution than traffic? The results were 57% industry and 24% traffic. So it turns out that I don't care, would you say that tiddlywinks contributes more or less to air pollution than cars? The tiddlywinks would be would contribute more than the cars because it was done first. So basically people are, whatever you say first is the answer that they chose. So, and that occurs just because, people will do that. They'll have a bias to which they'll answer. It's the first one that you say or the last one you say. If there are a whole bunch of options you give them, then they always pick the last option because it's the last one that they remember. Okay, so potential pitfalls, non-response. So non-response occurs when either someone refuses to respond to a survey question or is unavailable. So people who refuse to talk to pollsters have a different view of the world around them that is markedly different than those who let pollsters into their homes. So exit polls. So when people vote for a particular person in office, usually the way that we get results is that, the particular television station or whatever, will, I wonder why that happened. Okay. Oh, that mark, that's only there. Okay, they will ask people who they voted for. So they have these, what are called key precincts. And so they figure out sort of, I'll tell you later, I guess. But these, what are called key precincts. And then they will ask a certain number of people who they voted for after they voted. And it turns out that in some elections, they have discovered that the people who voted for particular people were less likely to answer who they voted for as compared to others. And so because of that non-response rate, some exit polls incorrectly determine the strength of who was actually leading in a particular race. So next, missing data. So missing data can dramatically affect your results, and they can drop out for a variety of reasons. So, examples. People with low income are less likely to report their incomes. So, people who are homeless, low income, minorities, are less likely to be included in the US Census. Another potential pitfall. If I can, no, I'm not going to do that. Okay, so yeah, there it is. Okay, well, another potential pitfall. Precise numbers. Just because a figure is precise, this does not mean that it is accurate. A precise number can be an estimate. It's just that you've written it to more decimal places. So precise numbers, if a precise number is an estimate, you should refer to it as an estimate. So in this class, a lot of times, I may be asking you to write your answer to 8 decimal places or whatever. That does not mean that it is accurate to 8 decimal places. That just means that I want you to write that out to that many decimal places so that we can check if your technique is correct. So we're really looking at your technique. This is not how it should be reported outside of a statistics class. Oh, percentages. So percentages can be quite misleading. So Continental Airlines ran an ad claiming, "We have improved 100% in the last 6 months with respect to lost baggage." So what does that mean? So in other words, does it mean that they have no mistake and no missing baggage? Or not really sure what 100% improvement means. Okay, so similarly, your sales can improve 100%, but maybe last year you had a sale of $1. This year I have a sale of $2. Well, that's 100% improvement, but maybe it's compared to someone who has $1 billion one year and sales of 1.5 billion the next year. Well, the 100% improvement doesn't look as good as the $500 million improvement. If you're just comparing percentages, it seems like the other one is better. So, a random variable. Random variable is usually denoted by RV, random variable. A random variable is a function whose domain is called the sample space. And so an example of a random variable is, what was it? Height. So I said height. And so height could be a random variable. Data is the particular specification of a random variable. And so data is a set of numerical or categorical values obtained from a particular variable. So such as, let's say 5 foot 4 inches. That could be data, and 5 foot is another data for the height of students from this class. So quantitative, there are 2 ways to, so there are different ways to categorize data. One way is quantitative data and qualitative data. So quantitative data is data that consists of numbers representing either counts or measurements. So an example of that would be weights of supermodels, ages of respondents. So that would be an example of quantitative data. We could also have qualitative data. So my data could either be quantitative, a number, or qualitative. Qualitative, sometimes also called categorical or attribute data. There's also attributive data. Okay. And this is data that can be separated into categories that are distinguished by some non-numerical characteristic. So for example, the gender of a professional athlete. So that is some qualitative data. Notice that it is non-numerical in characteristic. And so even if you put a number to the gender, say 0 for male and 1 for female, it still is non-numerical in nature. This fact that you put a number next to it doesn't mean that the number makes any sense. Similarly, shirt numbers on a professional athlete's uniform. That is non-numerical in nature, even though it's a number. Number 25, on your shirt, doesn't signify anything other than it's your name. So this is really a substitute for a person's name. They didn't want to put, a long name on the back of the jersey because you can't see it from, if you're very high up in the bleachers, you're not going to be able to read someone's last name, first and last name on their jersey because it's too far away. You can see, maybe 2 big block numbers you can probably distinguish, but that's about it. So the fact that they put a number on your uniform is just because that is your name. And so therefore, it is qualitative data. Next, we can further subdivide quantitative numerical data into 2 different categories. So my numerical data, quantitative data, can either be discrete data or continuous data. And so discrete data is data that results from counting. And so if you obtain your result through a process of counting, then it is discrete data. So an example is the number of eggs that a hen lays. Continuous data. So one type of numerical type of data is discrete. Another type of numerical data is continuous. So we have this continuous quantitative data. If the data is obtained by measuring. And so if you measure, it is continuous data. If you count, it is discrete data. So an example would be the amount of milk that a cow produces, 2.343115 gallons per day. So that is continuous. What you notice is that with continuous data, you measure with an instrument. And so continuous data has an instrument and you measure with that instrument. Whereas discrete data, you count. So notice that if you're looking at how much milk a cow produces per day, you could do it in gallons. You can do it in, oh, I don't know. Let's say, oops. And so you can do it in gallons, you can do it in liters, you can do it, things of that sort. So if you change your instrument, say from liters to gallons, if you get, a different result, one is 2.4 gallons, the other is 5.2 liters, then that is continuous data. Whereas it doesn't matter, if you're asking how many eggs a hen lays, there's no instrument there. You're not measuring, there's no, if you put a different instrument there, you're not going to get a different answer. It's the number that they lay. So, discrete variables are obtained by counting. In general, discrete variables will assume values that are whole numbers. Continuous variables are obtained by measuring. In general, continuous variables can assume all values in a particular interval. So, one way of categorizing variables. Quantitative, well, let's say it this way. The one way of categorizing variables. Qualitative variables, where you measure, and quantitative variables, where you're going to count. And those continuous and discrete are called quantitative variables because you are somehow, they involve numbers. So you have qualitative, quantitative, and quantitative can be further subdivided into continuous and discrete. Now, there's another way of categorizing data, and it is with the amount of mathematics that I can perform on the data. These are called levels of measurement. And so we have several different types of levels of measurements. And so this classifies data by the amount of mathematics that can be performed on the data. So there's nominal data, ordinal data, interval data, and ratio data. So let me go over nominal data. So in nominal data, you can only categorize your data. So the only thing you can do is categorize your data, and you can't do any other mathematics with it. So you can't add, subtract your data. You can't order your data. You can't figure out if a particular piece of data is bigger than another particular piece of data. If there's no way that there's a total ordering on your data, then we say that is nominal. So the nominal level of measurement is characterized by data that consists of names, labels, categories. The data cannot be arranged in an ordering scheme, such as from low to high. You only know set inclusion on nominal data. The nominal level of measurement classifies data into mutually exclusive, meaning non-overlapping, exhaustive categories in which no order ranking can be imposed upon the data. So with nominal data, only set inclusion can be determined. And so basically nominal data is where you can just have you can only determine set membership. So example, if the survey responses are yes, no, undecided, that's nominal data. Ordinal data. So ordinal data is where not only can you determine what category you're in, you can also tell if one is bigger than the other. So there's some way to order things. But you can't do any arithmetic with it. So you can order things, but you don't have any sort of arithmetic that you can perform on these. So data that are at the ordinal level of measurement, if they can be arranged in some order, but differences between data values either cannot be determined or are meaningless. The ordinal level of measurement classifies data into categories that can be ranked. However, the precise difference between the ranks do not exist. So with ordinal data, the set is totally ordered. However, the difference between two elements of the set is unable to be defined. So, for example, course grades, A, B, C, D, F. So I can determine if your exam had a grade of A or B on it. But if you look at differing grades on people's exams, and you say, well, what's the difference between the person who got an A and the person who got a D? Well, you can't, say, well, is that the same as the difference between a person who got a B and an F? No, I mean, there's no way to tell what the difference is between those. So you can't define a difference on these particular grades. Interval. So in interval data, you can define differences. So differences are defined. But 0 is meaningless. So if you don't have a really meaningful 0, then it is interval data. And so interval level measurement is like ordinal level with the additional property that the difference between any two data values is defined. However, data at this level do not have a natural 0 starting point, meaning that 0 does not imply that none of the quantity is present. The interval level of measurement ranks data, and precise differences between units of measure do exist. However, there is no meaningful 0. So with the interval data, differences between any two elements of the totally ordered set is defined. However, scale and multiplication is unable to be defined. And so if you look at, say, the year 1000, the year 2000, well, 2000 is 1,000 years after 1000, but it's not twice the age of 1000 or whatever. It's not, it doesn't make any sense. Similarly, 1776 is 776 years after 1000, so that makes sense. 1492 again is 492 years after the year 1000, but you can't take the ratio of these two, it wouldn't make any sense. You can't, say that this is, 12% bigger than this or whatever. It doesn't make any sense. And again, saying the year 0 doesn't mean that you have no years or whatever. Doesn't really make sense. So ratio data. So in ratio data, 0 does make sense. 0 means none. And so the ratio level of measurement is the interval level of measurement with the additional property that there is a natural 0 starting point. So 0 indicates that none of the quantity is present. For values at the ratio level measurement, differences and ratios are both meaningful. So the ratio level measurement possesses all the characteristics of interval measurement, and there exists a true 0. In addition, true ratios exist between different units of measurement. So with ratio data, the difference between any two elements of the totally ordered set is defined, and the scalar multiplication is defined. So an example would be the height of a student. So you notice that if a student had 0 height, then that means they would have no height. So 0 in this case is meaningful. 0 means that they have none of the quantity. Similarly, the price of a college textbook. So 0, if your textbook costs $0, then it has no cost. A $100 textbook costs twice as much as a $50 textbook. So again, this ratios make sense. Scalar multiplication makes sense. So in summary, we have nominal levels of measurement. We can tell what category it's in. Ordinal level of measurement. We can tell what category it's in. And these categories have order. Interval level of measurement. So we have a difference, but no natural, 0. And ratio level of measurement. We have differences and a natural 0. So examples of measurement scales. So nominal level of measurement. So zip code. So zip code, well, you can tell what zip code you're in, but you can't take differences of zip codes, and it doesn't make any sense. Similarly, you can't order zip codes, the fact that you're a 91324 and someone else is at 14215 doesn't really, that doesn't say that, one is bigger than the other or one's less than the other. There's no ordering to this. Similarly with gender, you can tell if you're male, female, but you cannot order these. Same with color, eye color, blue, brown, green, hazel, etc. You can tell what your eye color is, but there's no way to order, these colors. Political affiliation. So you can tell what political party you're in, but again, you can't order those. Religious affiliation. Again, you can, tell what religion you're in, but you can't order those. Major field. So you can tell what field you're in, but again, you can't order those. Unless you're in mathematics, in which case, number 1. Nationality. Again, you can't. You can tell what nation you're in, but you can't order those. Ordinal level of data. So grade, A, B, C, D, F. Well, it has an order, but you can't take the difference. If you're in first place, second place, etc. Again, that's an order, but you can't take the difference. Rating scale. poor, good, excellent. Again, you can order that, but you can't take the difference. A ranking of tennis players. Again, you can order that, but you can't take differences. SAT score. So interval level measurement. So SAT score, you can certainly take the difference. Your score is 100 points higher than someone else. But SAT score of 0 doesn't mean that you had no score or whatever. As a matter of fact, I think if you answer nothing on your SAT, you have a score of 400, I believe. IQ. So your IQ is, again, you can tell differences. This person has a IQ that's 10 points higher than someone else's. But an IQ of 0 doesn't mean you have no IQ. As a matter of fact, the way that the IQ scale is determined is that they look at white adult males, and they look at all those people in the United States, all those adult males, adult Caucasian males that took the IQ score, and they take the average of that, and they make that 100. And so the average on your IQ score is normalized so that it has a score of 100. And there's something called the standard deviation, which is a measure of how spread out the data is. And they make the standard deviation 15 points. So that's how they figure out your IQ. So 0 doesn't mean that you have no IQ. It just means that you are many standard deviations below the average. So temperature in Fahrenheit or in Celsius. And so if you look at your temperature, let's say 100 degrees Fahrenheit, well, that, you can certainly take different, 100 degrees is 10 degrees more than 90 degrees Fahrenheit. But 0 degrees Fahrenheit doesn't mean that there's no temperature. It just means it's 0 degrees Fahrenheit. Ratio. So things that have ratio level of measurement are height. So if you have 0 height, that means you have no height. Weight. If you have 0 weight, that means you have no weight. Say time. If you have 0 time, that means you have no time. Salary. If you have 0 salary, well, that means you have no salary. Age. If you have 0 age, that means you have no age. Temperature in Kelvin or Rankine. And so if you have, say, 0 degrees Kelvin, that means you have no temperature. Okay, so independent variable. An independent variable is a variable that is systematically manipulated by the experimenter. Dependent variable. The dependent variable is a variable that is influenced by the independent variable. So let me give you a summary of what we've done in this section. So experimental design. An experimental study or an interventional study assigns participants to receive a particular exposure. Assignment is primarily distinguished between the experimental. So assignment is the primary distinction between the experimental study or other study designs. Experimental designs are used to study are used to test the efficacy of new, let's say, medications, vaccines, medical devices. They are also used to test the effectiveness of preventative interventions, diagnostic methods, treatments, protocols, rehabilitation therapies. Most experimental studies randomly assign some participants to an active intervention group and others to a comparison group, so that the results in the two populations can be compared. Experimental studies require careful design and oversight to ensure that they minimize the risk to participants and do not violate other standards for ethical research and practice. So, observational studies. An observational study does not intentionally expose any participant to an intervention or ask any participant to change their behavior. Examples of observational studies are case studies, cross-sectional studies, case control studies, cohort studies. If the goal is to describe the health profile of a population or to examine whether a particular exposure is associated with an increased risk of an adverse health outcome, the best design is probably an observational one. So, epidemiology is the study of the distribution and determinants of health in human populations. Most epidemiological studies are observational. So, a descriptive epidemiological study. So, descriptive epidemiology studies are observational studies that quantify how often various health-related exposures or outcomes occur in a population. They're used to characterize the person, place, time factors associated with a particular type of adverse health outcome. Descriptive studies answer the questions like what, who, where, when. Examples of descriptive studies are case studies or cross-sectional studies. Analytic epidemiology studies. Analytic epidemiology studies seek to identify the risk factors or the protective factors for various adverse health outcomes, or to test the effectiveness of interventions intended to improve health status. Analytic studies answer the questions like why and how. Analytic studies are often used to test the hypothesis about causal and protective factors that were generated by your descriptive studies. Example of analytic studies are case control, cohort, or experimental studies. So, a case series study. A case series describes a group of patients that have the same health condition or who have undergone the same procedure. So, let me go through this diagram. So, time or research limitations. Yes, then you should collect. Are you collecting new data? Well, let's say no. Then you do a secondary or tertiary study, meaning that you're studying what other people have done. Yes, so you're not collecting new data. Yes, you're collecting new data. So are you doing an experiment? Let's say no. Then are you looking at exposure, the disease, or the population? If you're looking at the exposure, you do a cohort study. If you're looking at the disease, you do a case series or a case control study. If you're looking at the population, you do a cross-sectional or cohort study. If you're doing an experiment, well, you do an experiment. So, in a case series, the goal is to describe a group of individuals with a disease. In a cross-sectional study, the goal is to describe the exposure and or the disease status in a population. Case control study is, the goal is to compare exposure histories in a population with the disease, the cases, and with people without the disease, the controls. A cohort study. The goal of a cohort study is to compare rates of the new disease, the incident rates, so the incidence in people with a different exposure, with different exposure histories, or to follow a population forward in time to look at the incident rates of the disease. So an experimental study. So the goal is to compare outcomes in participants assigned to an intervention group or to a controlled group. A qualitative study is the goal is to seek to understand how individuals and communities perceive and make sense of the world and their experiences. An ecological or correlational study. The goal is to compare average levels of exposures and disease in several populations. A review or meta-analysis. The goal is to synthesize existing knowledge. So a primary. In a primary study, the goal is to collect and analyze new data. A primary study collects new data from individuals, whereas in a secondary study, the goal is to analyze existing data. So a secondary study analyzes existing data set or existing health records. Tertiary. So in a tertiary study, the goal is to review and synthesize the literature. A tertiary study reviews and synthesizes existing literature on the topic. Okay, so. If you select participants based on the disease status, if you have no comparison group, that's a case series. If you have a comparison group, that's a case control study. If you select participants who represent a population, if you're doing it at one point in time, it's cross-sectional study. Multiple points in time, it's a cohort study. If you select participants based on the exposure status, if you observe the exposure, it's a cohort study. If you assign the exposure, it is an experimental study. Okay, so researchers who have access to occupational records may prefer to choose a cohort study design that compares health outcomes among exposed and unexposed workers. This type of cohort study approach is especially valuable when exposure is rare in the general population, but high in the occupational population. Researchers who have access to clinical records may prefer to choose a research question that can be answered by a case series or case control study. Those study approaches are particularly valuable when the disease is relatively rare. Researchers who have access to a unique population group from which the representative sample can be drawn often choose a cross-sectional or cohort study design that enables them to understand the health status of that population. So just looking at the duration of the study, if all the data is collected at one time, it's a cross-sectional case controls study. If it's during the study duration, so most studies are collected at one time, but some follow participants forward in time. So it's during the study duration. It's a case series or qualitative study. If it's a really long period that you've done these, so a participant must be followed forward in time. It's a cohort study, experimental study. So overarching macro level frameworks that offer principles of reasoning with particular paradigm assumptions are legitimate various schools of research. Methodologies must provide both strategies and grounding for the conduct of the study. One of the most crucial factors involved in the selection is familiarization. So your methodological design needs to address the question, be within your capacity and interest, be practicable and doable. So the actual micro level techniques used to collect and analyze the data. The methods of data collection include interviewing, surveying, observations, and some unobtrusive methods, while the methods of analysis comprise some quantitative strategies, in other words, statistics. Qualitative strategies, which are more thematic. These are usually non-numerical in nature. So tools. Devices used in collection of research data include things like questionnaires, observation checklists, interview schedules. So